Hey folks, how's it going? This is Mr. Murray coming to you with a Do Now for Course 1 Honors for Thursday, April 16th, 2020. Now, we've just kind of started to put the finishing touches on our unit on quadratics, and that was a really awesome unit. I hope you enjoyed it and that you took a chance to finish things up, take a look at your little assessment and see how you did. And it's likely that we will revisit that at the sometime later on in the year. So if that was a challenge for you, that's okay. We will revisit it, but just make sure that you feel really good about it and reach out to me if you want additional help. Okay, but now I'm going to start to dabble in something new. And this gets back to a problem that we talked about right at the beginning of the year. So we're coming kind of full circle, so to speak. At the beginning of the year, I gave you some of these sets of numbers, these sequences, so to speak, of numbers. And I asked you to fill in the blanks by finding a pattern. So I'm going to ask you to do a similar thing here. So what we're going to do in a moment is you're going to figure out what numbers have to go in these blanks if each of them follow a set pattern. So this is going to follow, if you look at a pattern, this will follow a pattern. This will follow a pattern. This will follow a pattern, okay? So take a moment, see if you can find out what the pattern is, and use that to fill in the blanks, all right? And then when you're ready, unpause, and I'll show you what I got. All right, so here's what we're going to do. We take a look at this sequence. We can see that we're going up by 4, up by 4. So if we continue to go up by 4, this will be 13. This will be 17. This will be 21. Okay? And this is what we call an arithmetic sequence. Okay? We can see that it always has a common difference. It's always going up by or down by the same amount, being added and subtracted. And if we think about a rule for this, well, we can think of this as a linear function, right? Because a linear function always changes by the same amount. This linear function is going up by 4, and remember that kind of represents the slope. And then think about it. If I plug in, let's say 1, what would I get? Well, right now I would get 4, right? Because 4 times 1 is 4. But what I want to get is 1. And so for that to happen, I have to put a negative 3. So it's like a y equals mx plus b. What about this next one here? Here I jump twice and go up by 14. So with a linear function or an arithmetic sequence, we can always assume the jumps are the same. So if I went up 14 in 2 jumps, I went up 7 in 1 jump. And because it's a sequence, the pattern continues even if I don't know what's going on past here. I still know, because I found it goes up by 7 here, it's going to continue to go up by 7. Here I jump twice to get 21, and then jump 3 times to get 51. What if I wanted to figure this part out? Well, if I jump 3 times and go up by 30, then each of the jumps had to be 10. Because it's a linear rule, it's an arithmetic sequence, 41 rather, it's an arithmetic sequence, so the common difference is common, it always stays the same. Okay, and we could also make up rules for these. So we know the common difference here, what it's going up by, is 7. And if I plug in 1, well, I get 7, I need to get 1, so I have to put a minus 6. And you can imagine, right, if I plug in 3, for example, 3 times 7 is 21, and notice if I subtract 6, I get to 15. Similarly, right, we could do this one. This one is 10n minus 9. And you can see if I plug in 1, 10 times 1 is 10, minus 9 is 1. But this last one is different. I'm not adding. See, 2, 6, 19. Darn. Actually, I think this would be 18. 2, 6, 18. That's weird. These aren't going up by the same amount. But do we see a pattern here? What could they be doing? Well, we're not adding, we're multiplying. 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. So if I continue to multiply by 3, what's 27 times 3? It's 81. And 81 times 3 is 243. 8 times 3 giving me 24. 1 times 3 giving me 3. But notice, this is not working. But here's what I'm thinking. Well, if I keep going like this, I still do get a cool pattern with my common differences. What's happening to the differences? What's 2 times 3? What's 6 times 3? What's 18 times 3? What's 54 times 3? So a cool thing's happening with the differences, but they're not staying the same. And because of that, we cannot use this rule, right? We can't use the arithmetic rule. But what happens, what do we call it when you multiply a number over and over? What do we call 2 times 2? Right? It's 2 squared. What do we call 2 times 2 times 2? It's 2 cubed. What do we call 2 times 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 2? Well, there's 10 of them, right? So it's 2 to the 10. Right? So this is what it looks like when we multiply over and over. So what are we doing? Well, here we're multiplying by 3, then by 3, then by 3, then by 3. And what does it look like to multiply 3 over and over? Now it looks something like this. And so as we're going to find out, this rule is to these kinds of sequences as this rule is to these. Now, if I plug in 1 rather, I get 3. So what we're going to learn is this is actually, believe it or not, what if I told you that this is 1/3 times 3 to the power of n? Well, when you plug in 1, 3 to the first is 3. And 1/3 of 3 is 1. When you plug in 2, you get 3 squared. 3 squared is 9. 1/3 of 9 is 3. When you plug in 3, you get 3 times 3 times 3, which is 27. 1/3 of 27 is 9. And this is what we call an exponential function. And why do we call it that? Because now, where are you plugging into? You're plugging into an exponent. All right, so that's where we're going to head today. And so in today's activity, you're going to examine one of these sequences. And I want you to try to use what we've learned so far about arithmetic functions with regard to how we would find an explicit rule and maybe a recursive rule, if you can think about that, and look for some hints in the notes. And see if you can also figure out how to make that work for an exponential one. All right, best of luck today. Hope you're able to get it. I know you guys can do it. Have a wonderful day. I'll see you at the Hangout. Take care.